This is the first of 3 videos introducing you to the lights out game on graphs. So in this first video, we're going to give you an introduction to one of the lights out games that are possible on graphs. One of the things that I'm not going to talk about in these videos, but we can talk about later, is that there are many different versions of lights out that we could look at. And this is just one particular game, just to give you an introduction. So the first thing we're going to do is describe the original lights out game from about, I don't know, almost 30 years ago. We're going to show how that particular game can be generalized to graphs. That's where the math comes in. And then we're going to define graph labelings, and that is going to enable us to generalize the game even further to when the lights have more than one color. So the original game was actually an electronic game. So you have a 5x5 grid of lighted buttons that can be pushed. So you turn on the game, some of the buttons are on, some of the buttons are off. When a button is pushed, then that button, along with every button that's right next to it, and when I mean right next to it, right above, right below, just to the right or just to the left, they switch from on to off or vice versa. Whatever they were before, they're different now. If they were off before, then they're on now. If they were on before, they're off now. And then the idea is we want to push all the buttons so that, not all the buttons, but push the buttons until all the lights are off. So here's a slightly simpler version of the game. Instead of 5x5, we're going 3x3. Some of the ones are on, that's going to be the orange ones, and the blue ones are going to be off. And so we want to push the buttons so that all of them are blue. So we're going to start by pushing that one in the lower left where the arrow is pointing to, V7. Notice that V7 is right adjacent to V8 and adjacent to V4. So when we push that button, V7 and the two right next to it will change. So the V4 will change orange, V7 and V8 will change blue. Is that right? Yeah, nice one. Then we're going to do the lower right, V9. That one is also next to two other buttons. It's right next to V8, so it's going to turn that one orange. It's right next to that V6, that'll turn blue, and then V9 will turn orange. There we go. Now when we push V6, that one is adjacent to 3 buttons, right? It's adjacent to V3, V5, and V9. Those are all going to change. V3 and V6 will change orange. V5 and V9 will change blue. Next, we'll hit V2. That is also adjacent to 3. So V1 and V3 will turn blue. V2 and V5 will turn orange. And then I'm not going to give an arrow for the last one because it's right in the middle. We're going to hit V5. And when we do, all the lights go off and we've won the game. So let's see if we can think about what makes the game work to see what's going to enable us to generalize this game to graphs. Well, first of all, we need lights. If we don't have lights, we can't play the game. And those are going to be, when we define graphs, those are going to be our vertices. We need to know whether or not a given light is on or off. And that may change in the course of the game. And that is going to lead us to talk about labelings. We're going to have to label each light on or label it off. And we may change those labels every time we toggle a vertex. We need to know when we push a vertex, when we toggle a vertex, what vertices are going to be affected. Of course, the vertex that is being toggled will be affected, but also the ones that we consider adjacent, right? So whatever our mathematical structure is, it's got to take into consideration these adjacency, and that leads us to edges. And so this leads us to the definition of a graph. So a graph is just a pair of sets. V is the set of vertices, E the set of edges, where V can be a set, literally any set. We call it the vertex set. And the elements of V, in the context of being part of a graph, are called vertices. And then the set E is also a set, but that is a set of pairs of elements in V. It's pairs of vertices. So these are unordered pairs because we consider their relationship to be symmetric, and these pairs of vertices are called edges. Now, when we visualize, and for lights out, how this corresponds is the vertices are the buttons that we're pushing, and the edges are all the pairs of buttons, all the related buttons that change each other's states when pushed. So if I push a button, it's going to change itself and any vertex that it's adjacent to, that it shares an edge with. So the last thing that we have to worry about in this game, however, that wasn't taken by the definition of a graph, is we have to keep track of what states the lights are in. Are they off? Are they on? So we will say that a light has state 0 when it is off and state 1 when it is on. That'll be convenient to us because then we can talk about turning lights on and off as being something that's computational. And that leads us to the definition of a graph labeling. So again, G is a graph, V is the vertex set, E is the edge set. And a labeling of the vertices is a function, we'll call it pi, from the vertices to, well, to something, where that something is either the integers, they could be labeled with integers, or elements of zk, they could be they could be labeled with elements of zk. We're going to be looking at zk for lights out, but ordinarily labels are often labeled by with integers. So what pi does is, if you have a vertex, whatever pi maps the vertex to, that's going to be the color of that vertex. That's going to be the label of that vertex. So for lights out, we are looking just at 0 and 1. 0 is off, 1 is on. And so we're looking at labelings from V to Z2, because Z2 just consists of 0 and 1. All right, so let's go ahead and play this game on a different graph. This one isn't a grid like the original one we did. So here we have a graph where the edges are just the lines between the vertices. Notice that 2 of the vertices are off. That's the 2 zeros that you see there. And 3 of them are on. That's the 3 ones. So if we hit this vertex over here on the left, that is only adjacent to the one right next to it. So it's going to turn its own label to 1 and the one right next to it to 0. When we hit that one right there, that one's adjacent to 3 vertices. It's going to turn the ones right next to it to 0, and the 0 adjacent to it to 1, and it's going to turn itself into 1 as well. And we can continue doing this. We hit this one's adjacent to 2 vertices. It's going to change all those when we hit it. And then we hit the one on the very right end. When we hit that once, it changes the last 2 back to 0, and we've won the game. So that's how it's played on just a general graph. All right, so if we want to describe this game graph theoretically, here's how we would do it. So and again, we're not going to have any pictures here. We're just going to describe the game as it relates to being a graph. So G is a graph with vertex set V, edge set E. We start with some labeling of the vertices, so we'll call that pi 0, going from V to Z2. So that's the initial labeling. And then what we're going to do is we're going to toggle some vertices, and that is going to change the labeling of the graph as we toggle it. So I want to sort of describe how it works in general. So let's suppose we're at some point of the game. We could be at the very beginning where our labeling is pi 0. We could be in the middle of the game. We could be towards the end of the game. But suppose that at some point during the game, we have a labeling pi from V to Z2. And then suppose we pick one of the vertices, little v, and we toggle that one. And what that is going to do is change the labeling to some other labeling, and we'll call that pi prime. And the rule for that labeling is pi prime of w is equal to, well, if w is either equal to v or adjacent to v, we increase the label by 1, so pi of w plus 1. And what that does is, if the original label was 0, the plus 1 will change it to 1. And since we're in Z2, if the original label was 1, adding 1 will take us back to 0. So it does exactly what we want it to, again, in a computational way. And then if w is not v and is not adjacent to v, then we just end up with pi of w, just the label that it was before. So the top line says if it's equal or adjacent to the vertex we're toggling, we increase the label by 1, and if it's not, then we leave the label alone. And we win the game when we have achieved the labeling, I'll call it pi sub f, where pi sub f of v equals 0 for all vertices v. Right? That's when all the lights are off. All the vertices are off. So I'll give you a little history of this game that we're playing with just Z2, right? So this was the first place where really this was studied is, well, this is not exactly lights out. It's something very similar. It's by Pelletier in 87 and Stock in 89. They looked at a game called Merlin's Magic Square. Fun fact, I actually played this game when I was a kid, back in the, late 70s, early 80s, something like that. And that is a game which is very similar to Lights Out. It's not exactly Lights Out, but it's very similar. And they use very similar methods to solve it. They use matrix methods, which I'll explain in a couple videos down, but they use matrix methods to find solutions. In 1989, Suttner studied the lights out game that we are now familiar with. He looked at it from a computer science point of view. He looked at it using cellular automata. And he proved, among other things, that the lights out game can always be won if we start off with all the vertices labeled with 1. One fact that I did not let you know is it's actually possible for you to lose the game, not be able to win the game, if I give you an unfriendly initial labeling. But Suttner said that if all the lights are on at the beginning of the game, you can always win. And then Almond, Slater, and some others studied something called parity domination of trees and cycles, other types of graphs. They didn't know, either they didn't know or they didn't care that they were looking at the game Lights Out. Parity domination turns out to be equivalent to playing the Lights Out game. They used a bunch of elementary matrix methods as well, and they concentrated on something called all parity realizable graphs. When we look at those on Lights Out, those correspond to graphs that are what we call always winnable. We'll get that to in a little bit. Well, not a little bit. Again, a couple videos down the line. Goldwasser and Klostermaier also studied parity domination, but they also understood the connection between parity domination and the Lights Out game. And as far as I can tell, they're the first to actually point out that connection. Anderson and Field in 1998, they used matrix methods to solve Lights Out games. And as far as I can tell, they're the first to actually apply that. And so again, we'll see some matrix methods in the linear algebra video. That's the third video in this series. And so you'll see what they were talking about. And then there are other people who looked at some variations on the Lights Out game. Looked at the Lights Out game and said, yeah, that's a fun game, but let's do something funky with it. Araujo did something like that back in 2000. And the three-person team of Kraft, Miller, and Pritikin did something similar in 2009. So we have a Lights Out game that we can play on graphs. Can we generalize it even further? Well, yes, we can. What if we try to play the game, for instance, if we have more than one on label to put on the vertices? So you could think of it as not only are the lights on, but they can also be different colors. So instead of labeling our vertices with Z2, where we just have an off color and an on color, we will label it with ZK, where K could be any integer that is at least 2. And that opens us up to the possibility of having more than one color that is on. So we consider 0 to be the off label, and then the other K-1 labels are considered to be on. And again, a good way of visualizing that is we could think of those K-1 labels as being K-1 different colors that our lights can have. When we toggle vertices, it works exactly the same as our original game, except now instead of going back and forth between on and off, we cycle through the labels until we come back to on at the end of that cycle, or come back to off at the end of that cycle. And then, of course, as before, we win the game when all the vertices are off. So we're going to describe this graph theoretically. It's going to look very similar to what we did for Z2. In fact, the only real qualitative difference is where we used to have a Z2 in the Z2 game, we're going to have ZK instead. But everything else is going to be pretty much the same. So we start with some initial labeling, and then we keep toggling vertices. If we're somewhere in the game where we have some labeling pi from the vertices of G to ZK, then when we toggle the vertex little v, that changes the labeling to pi prime, and the formula for pi prime is going to look very similar as before. Pi prime of w is equal to pi of w plus 1 when w is either equal to v or adjacent to it, and it's just plain old pi of w otherwise. And what that says, that pi of w plus 1 moves the color of that vertex, or the label of that vertex, to the next one in the cycle. And if it's not adjacent, it's not equal, then it just leaves it alone like before. And as before, the game is won when we have achieved the labeling where the labels are 0 for all the vertices. All right, so here's an example of playing the game. Here we're going to have 4 colors, if you include off as being a color. So we have 3 colors that are on, number 1, 2, and 3. So all the vertices you see, the lights are on, but they have a bunch of different colors. So if I hit this vertex, I'm going to hit that one. I think I'm going to hit that one 3 times, right? And each time I hit the vertex, that vertex and the ones right next to it will increase by 1. Notice when I hit it the first time, that 3 turns into a 0. That's because we have 4 colors. When we get to 3, we cycle back down, around to off, right? So when we hit it again, that 3 on the lower left is also going to be 0, but that 2 in the upper left is going to turn into 3. And then the vertex we're hitting itself is going to go up to 1. And then we'll hit it one more time just for fun. And that's the labeling we end up with. Now, if we go down here to the lower left, we're going to hit that one, I think 3 times again. So again, we hit it once, everything increases by 1, or those 2 increase by 1. We hit it again, the 3 increases by 1, but to 0 because we cycle around. And then we hit that one more time. The 0 turns into a 1. The 3 turns into a 0. Hooray. Now we're going to hit this one on the center right. We're going to hit that one, I think, 3 times as well. Again, everything sort of cycles around until you get to its terminal color. We hit this one. We're going to hit that one 3 times, I think. So that and the green one are going to be increased by 3. 1, 2, 3. And then finally, we're going to hit this one twice, and that will take both of them to 0, because one takes them to 3, another one takes it to 4, but 4 is 0 in Z4. And then, hooray, we won the game. So that gives you an idea about how the lights out game works. In the next 2 videos, we're going to talk about some button pushing methods to help us actually prove some theorems about the lights out game. And then the third video is going to talk about using linear algebra methods to solve them.